This will be a walkthrough of 5.5 bending strength of compact shapes. Um, and we've talked about what compact shapes mean. Compact shape is a shape with low enough width to thickness ratios on the flange and web, so that if properly braced against lateral buckling and lateral twist, the shape can reach plastic moment capacity. So it is possible for a compact shape to reach plastic moment capacity, the greatest moment it could ever provide. And then there are two other moments that will be a function of the lateral torsional buckling unbraced length, which is L sub B. Okay. So what we want to focus on now is we're going to assume that everything is compact, and then certainly we check it, but for compact shapes we're then going to look at primarily unbraced length L sub B, and then we're going to look at this moment gradient factor, the C sub B factor, that will provide an increase in moment capacity, but again, moment capacity can never exceed the plastic moment capacity, right? M sub P ZX times Fy, right? The plastic section modulus ZX times Fy. All right, and there are certain cases or certain conditions where C sub B is beneficial. If you don't use C sub B, you just may be conservative, okay? It can never hurt you to not use C sub B, but it can help you if you do use C sub B, okay? So compact shapes, again, shapes that have a cross-sectional elements with low enough B to T ratios that the section can reach the plastic moment M sub P, okay, if properly braced, okay? So we check this off the list. We've determined that we check this off the list, right? We know it's compact, so now we can come and check the unbraced length to see if it's short enough that the nominal moment is plastic moment, right? And then the next part would be lateral torsional buckling, okay? Lateral torsional buckling is a function of the unbraced length, L sub B, okay, and it can be one of two types of lateral torsional buckling, elastic or inelastic, and then also we got to make sure the compact limits are made, okay, the local buckling, right? Again, this is if it's compact, all right. If it's not compact, then we have to go in and check flange local buckling and web local buckling. But section 5.5 assumes we have compact shapes. Okay, so again, remember I have a video on the width to thickness ratios, and I also have a video on lateral torsional buckling that AISC has provided, and I did the voiceover for you folks. Okay. So again, first things we got to do is we check the compact, non-compact, or slender conditions. Again, this is for our flange, this is for unstiffened elements, and this is for web stiffened elements, because I know of H over T sub W is for my web. And then I get that from this table B 4.1b, okay? We looked at previously B 4.1a for columns, okay? So unstiffened elements, case 10 for flanges of rolled shapes, okay? So there's our two limits that you see on the slide we just left. And then for stiffened elements, which are webs, all right, this is web, these are flanges. Here are our two limits for those, okay? Again, if lambda, which is the generic representation for this ratio, that's called lambda. This would be called lambda, Okay, it's just a generic term that we're going to use. Remember, we have the best we can have is compact. Then we have, I'm sorry, let me do it this way. We have lambda sub p, lambda sub p, and lambda sub r. If lambda is in this region, all right, if lambda is less than lambda sub p, it's compact. If lambda is greater than lambda p but less than lambda r, it's non-compact. And if lambda is greater than lambda r, it's then slender. Okay, and again, easy, I should say, difficulty or difficult. Okay, golly, I don't want to hit that button. All right, easy here, and then difficult. So we're starting with the easier part. Okay, and this isn't not too bad. Okay, this isn't too bad at all. Okay, so ideally we want compact shapes. That's the best we can hope for, is compact shapes, because that allows us the possibility of reaching full moment capacity. Okay, so once we know it's compact, we can use section F2, right, of the steel manual, and then we determine the moment strength based upon its lateral support, right, the L sub B. Okay, lateral support. All right, so the shorter the lateral support distance, the closer L sub B is to 0, the higher the moment capacity will be. So for continuous lateral support, which is the same as saying LB is 0, or we'll show later, it's really where LB is less than or equal to L sub P, we can reach the full moment capacity. Fy times Zx. Okay, thought I had an error there. Okay. So again, table B 4.1 for this, that's where we were when we looked at that. Okay. And then again, if LB is 0 or less than L sub P, we can reach that full moment capacity. Okay. Again, another reminder about the videos. All right. So again, if LB is less than L sub P, right, that's the same as saying continuous lateral support. My nominal moment capacity equals my plastic moment capacity. Okay. And if we use LRFD, we just take that plastic moment capacity and multiply it by phi. Okay. And again, this could be also written as phi sub B MP, because at this point, plastic moment capacity is my nominal moment capacity. If we're doing LRF or ASD, we divide by, and by the way, phi here is 0.9, same as before. And if we're doing ASD, we divide by the omega factor, and omega factor here is 1.67. Okay, so just very similar to what we did for everything else. All right, so lateral support or lateral torsional bracing does two things, right? Two different possibilities, which we talked about before. This type of bracing prevents horizontal movement. Okay, so the beam is essentially, the compression part of the beam is braced against buckling. Okay, this is what we call torsional bracing. Okay, it prevents the beam from twisting. Okay, and again, these represent bracing points. We always assume the supports are braced. Okay, so if you ever see no X there at the supports, it's assumed to be braced. Okay, again, take a look at that video. All right. So when our L sub B is less than L sub P, we reach full moment capacity, Zx times Fy. Okay. When we're greater than L sub P but less than L sub R, our strength is going to be based on inelastic lateral torsional buckling. And it's this equation here, which may look a little daunting, but it's not too bad. It's really a straight line. But if we get to an unbraced length L sub B greater than L sub R, then we are at a elastic lateral torsional buckling, similar to elastic buckling of a column. This is similar to inelastic buckling of a column. Okay. All right. So yeah, if we go to F2 in the steel manual, section F2, you'll see all this. Okay. So again, page 16147, section F2, doubly symmetric, compact eye shapes bent about their major axis. All right, so that means it's bending about the strong axis, okay, not the weak axis. There's a different section for weak axis bending. Yielding condition, that's one limit state. All right, one limit state of yielding is our plastic moment capacity. Again, assumes that it's compact. That's why we're here. All right, and then if we have that, if our unbraced length L sub B, notice it says yielding, but it doesn't tell you when it applies. It waits till we get down to lateral torsional buckling. And notice here it says when L sub B is less than L sub P, this does not apply. So then that means this controls. So again, I'm not sure why they decide to write it that way, but when L sub B is less than or equal to L sub P, you have plastic moment capacity. When we're in between LP and LR, we have this linear relationship. And again, notice this, 0.7 Fy. The 0.7 represents a reduction of 30% of Fy for residual stresses. Okay, so that means we're assuming we have 30% Fy for residual stresses. Okay, and notice it's S sub X. S sub X is elastic section modulus. Okay, then when we get L sub B greater than L sub R, we see something that should look a little bit familiar, F sub CR. F sub CR, F critical, is similar to what we had for columns, okay? And if you look here at what F sub CR is, it's quite a scary looking formula. And again, check this out, L over R, slenderness ratio, right, from columns, okay? This J, polar moment of inertia, S sub X, again, indication of section modulus, elastic section modulus. And then check this out, all right? This formula here, pi squared E over L over R squared. That you should remember from columns, okay? So F critical is very much the compressive strength or stress of a column, okay? And this part here adjusts for, I'll say quote unquote adjust, right, for the tension member, right? Since the tension member is keeping it straight, or the tension flange, I should say. So the tension flange tends to keep the top flange a little bit straighter than if it was all in compression, okay? And then last thing I'll point out to you is this value, or this parameter here, golly, change the color, C sub B, okay? And that's the other part of the lecture today, right? C sub B. Okay, so think of if C sub B is 1, this is all the nominal moment capacity. Okay. All right, so that's where all those formulas come from. Again, I would really encourage you to think of this as a column buckling. All right, slenderness ratio here, slenderness ratio here, and we'll show that this is a straight line relationship between M sub P and this value. Notice F sub Y times S sub X. All right, this is really a stress times section modulus, and that's really a moment strength. Oops, times section modulus. Okay. So let me show you one more thing here. So if I go to table T3, oops, was that that? That's not the one I wanted. Okay. All right, so let me pause it and fix that. Okay, I'm back. Magic of the digital world. Okay, so if I go to this table T3-2 or table 3-2, okay, it shows you all these values. Okay, it shows you LP, shows you LR, okay, and we can also calculate them, right? But most of the time students aren't too crazy about calculating them. It also shows you M sub P, shows you M sub R, okay, and we'll learn more about those shortly. Okay, so LP and LR, that's the main thing I want you to take note of. Okay, so now that's these values, right? LP and LR. Okay, so we have everything from the steel manual. Here's LP and LR also, so you can get everything you need for given a shape from table 3-2. Okay. All right, so inelastic, elastic, we saw that. Okay, so this is key. All right, so this is really the plot of the moment strength of a section. Right, plastic moment capacity, the max it can reach. All right, that's this one. Okay, so this is plastic behavior. This is inelastic lateral torsional buckling, and this is elastic lateral torsional buckling. So again, back to table 3-2, we see that these values are provided, and really what M sub R is, before I go further, let me go back one slide. This here is M sub R. Okay, this is M sub R, which equals 0.7 S sub X times Fy. Okay, so if I go to table 3-2, all right, and I pick out any beam, let's say the 14x30, I think I look at that one later. 14x30 has LP and LR of 5.26 and 14.9. Right, so this is 5.26 and 13.49 feet. So at those unbraced lengths, right, any unbraced length 5.26 or shorter is going to give me plastic moment capacity. MR, right, you can see MR is right here, and again these are multiplied by phi because it's for design, but there's our MR value. Okay, so I could take 110, 177. I just have to modify this chart to be phi M sub P and phi M sub R. So I already forgot what the values were, 177 and 110. Right, so this is 177 kip feet, and this is 110 kip feet. Okay, so again, you can think of these as data points, right? For an unbraced length of 13.49 feet, you have 110 kip foot moment strength. Unbraced length of 5.26 or less, you have a moment strength of 177 foot kips. Okay, now in between, right? Notice this is a straight line, okay? You can go to this table, again, table 3-2, and here's this phi BF, okay? Again, BF, something factor, I'm not sure what B represents, but it's the slope, okay? So 6.95. So what that means is this line slopes down 6.95 for every 1 foot increment in unbraced length. And this is really just that equation F2-2, right? So this is F2-1, this is F2-2, and this should be F2-3. Okay, and hopefully this looks like Euler buckling, right? Euler column, all right, because it is looking at an elastic buckling condition. Okay, notice here C sub B is 1. All right, so C sub B is 1. All right, again, I can't tell you enough. All right, so again, how do we get L sub R? Not so important. Certainly nobody's really crazy about calculating L sub R, but it can be done. Again, I'm not gonna put you through that, but you can find all these properties in the steel manual. But L sub R can be derived, okay? But usually not worth the effort, although it is a lot of fun. All right, so again, think of this as M sub R, okay? And L sub P is much easier to solve, okay? All right, so L sub P, again, is going to give you an unbraced length that we can have plastic moment capacity. All right, again, this is just a straight line of this equation here, this line, okay? All right, so in summary, right, L sub P, plastic moment capacity. This second one is inelastic lateral torsional buckling, and then this one is elastic lateral torsional buckling. Okay. All right, so then what I'd like to, okay, there I got inelastic, got ahead of myself there, elastic, okay? So we want to look at these tables, and actually I'm going to switch, well, let's see what, I can't remember what 12 by 30 or 12 by 40 is going to be, okay? So there's plastic moment capacity, okay? Again, hold on a second. All right, so we have the three equations there, and we can look at this table 310 and table 3.2 again. If I go to table 310, really this is a plot for every beam on this diagram. It is a plot of these three equations, okay? So again, if I look at, this equation, and this equation, which includes this one, okay? Those three equations really are represented here. So if I look at the, what did I say, the W12 by 30, okay? So if I look at the W12 by 30, it's right here. It starts out horizontal, so that's the first equation, right? That's this equation here. And then this second equation, which is a straight line, is really this portion, all right? Continues down, okay? And notice this value, if I come straight down, I'm at about 5.7 feet or so. But then down here at about 12 or 13 feet, this continues over to this chart, okay? And you got to be careful because these things are a little hard to follow, okay? These pages look like they're side by side, but they're not. This is page 3-123, and this is 3-125. So, and then notice it hits this open dot, and then it continues down, and it starts to curve. Okay, so this is the third equation. Okay, so again, if I go back to this equation here, okay, these three equations, we'll get, and we plot those, we get this one. And then for the 12 by 30, right, here's 12 by 30, okay, LP 5.36, L sub R 15.6, 12.56, again 15, right, 15.6, okay, and phi M sub P is 162, and then 101, 162, 101, okay. All right, so we've been here. I'm back to the wrong slide. We've been through there again, right? This is just a plot of that same line. Again, went back too far, so I'm slide 8, so I gotta get caught back up. Okay, so this is where we were, slide 11. Okay, so now that's the behavior of the moment strength of a beam based on unbraced length, okay, and being sure it's a compact shape. Okay, so again, inelastic, elastic, and then plastic moment strength. All right, so now C sub B. Okay, what is C sub B? C sub B is, I refer to as a moment gradient factor, because everything in the steel, when they do research, the best loading condition to generate a good consistent moment is one that provides a constant moment capacity or constant moment requirement, right? So again, if this is my M of X diagram and this is my location along the length of the beam, we showed previously in class that this is two equal loads, right, equally spaced. So C sub B is really geared towards this constant moment capacity, or constant moment requirement, sorry. All right, so when the moment isn't constant, that's when we start to see the moment gradient, right? Gradient means change, right? So that's when we start to see this value, okay? And C sub B is really helpful when L sub B is long and moment varies tremendously, okay? So it applies to a moment in single curvature. That means it's positive moment. This is positive moment. So that means it's a happy moment displacement, right? Single curvature. And if the moment within the unbraced length, so if this was our unbraced length, is constant, then C sub B is 1, okay? If the moment within the unbraced length is not constant, if it changes, then you can utilize this C sub B equation. And it really is all within the unbraced length. So again, maximum moment within the unbraced length, moment at the quarter point of the unbraced length, moment at the half point of the unbraced length, and moment at the 3/4 point unbraced length, okay? So it's really a helpful tool if you remember to use it and you use it appropriately. But if you don't use it, it defaults to 1, okay? And if L sub B is really short, the moment isn't going to change over a really short unbraced length. So the shorter the unbraced length, the more likelihood C sub B is going to be 1, okay? So again, if we look at this moment, here's our loading condition. And again, if I draw the moment diagram, it's going to look like this. Okay, and what this is telling you is if I have bracing at A and A, B, C, and D, the C sub B for this region is 1.67, and the C sub B for this region is 1.67, and it's 1.0 in here because my moment is constant, right? I'm braced here, 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 and here. Constant moment, C sub B is 1. Now, when I calculate C sub B here, I'm going to take this and get quarter points, right? This would be MA, this would be MB, this would be MC, and this is going to be my max moment, okay? MA, B, and C are at the quarter points of the unbraced length, and M max is the maximum moment on the unbraced length, and that would give you a C sub B of 1.67 using that previous formula. In through here, right, if I split this into quarters, moment's the same for every value of MA, and if I go back to here, and if all these values are the same, right, if MX or M max equals MA equals MB equals MC, then notice this 12.5, 2.5, add these up, 5.5, 9.5, 12.5. Then we end up with 12.5 over 12.5, so C sub B becomes 1. Okay? So it, numerically is consistent. Okay? All right, so we'll do this problem. I'll do it separately because this is getting long, I know, but I'll do this problem and get it posted also. Okay? But here's our loading and then our shear diagram. This is our shear diagram, so we can use that to calculate moments. Okay, so this problem is going to say if our bracing is at the ends only, that's part A, what's our C sub B? So at that point we have to get moment at the midspan, moment at the quarter span, moment at the 3/4 span. So that would be MA, MB, MC, and again this is going to be M max, right? This area under that shear diagram, that would be our solution for part A. Part B, now the bracing is at A, B, C, and D. So A, B, C, and D. So now I'm dealing with this portion, right? So I'm going to need my moment at the half point, moment at the quarter point, moment at the 3/4 point. Now the moment gradient is going to be closer to 1 here because delta M is smaller here than it was on the first example when it had a full unbraced length from A to D. Okay, so I'll get that posted, but I'm trying to get these lectures out to you so you have some help. Okay, all right, so C sub B, once we have C sub B, we take C sub B and multiply it by whatever moment strength we have out through here, right? So once we have our nominal moment, we just multiply it by C sub B, but this has got to be less than or equal to M sub P, right? You can never ever exceed plastic moment capacity. That's why these lines get dotted, because we can't use this, right? If I have a C sub B of 1, this is my equation. If I have a C sub B of 1.3, it magnifies the 1.0 equation by 1.3, but anything that gets above M sub P cannot be utilized. So it has this upper limit of M sub P. Okay. So again, one last time, I guess I kind of got ahead of myself before there, right? Summary of our unbraced length, right? If I go to table 310, right, I see there's my L sub P, and this is my phi M sub P. here is my L sub R, and this is my phi M sub R. And in between, right, this is a straight line segment, okay? And for that 12 by 30, it's gonna be 5.96 kip feet per foot, okay? All right. All right. And I think that, again, inelastic for this one, elastic for this one, and then plastic is our best case scenario, okay? Again, a lot of information, I understand that, but I think a lot of good stuff and hopefully helpful to you.